Welcome back, you guys. In this video, we're going to be looking at the relationship between momentum and Newton's second law of motion, and also the idea of impulse and what it is, its definition, and how we can use this idea of impulse, and also how it is. I'll go ahead and list it here. How it is similar to or akin to energy or work. And impulse is really dealt with in 9-3 in your textbook. We're going to address both of these in this one video here. And you have to bear with me, this one might be a long one because of the example that we're going to go through. First, to Newton's second law. I should recall a couple things. So we have the sum of forces that are acting on an object. And what Newton's second law says, at least how we looked at it, was F equals ma, essentially. So a net force is going to produce an acceleration. Now, rearranging this guy, we also have, I'm sorry, not rearranging, but we also have a relationship about acceleration being the change in velocity divided by a time interval in which that change takes place. So we could combine these two things and say to ourselves that the net force acting on an object is going to be equal to a mass multiplied by the change in velocity divided by, a change in time divided by a time interval, right? And this is going to give you something that you guys should recognize right away. You're going to see that, well, you have a mass multiplied by a velocity, or a change in velocity at least. And so there should be something about momentum in here. And that's true. We're going to get there in just a moment. What typically happens, sorry, let me back up a second. With Newton's second law, the way we initially looked at it here, we said to ourselves, well, really, the mass has to be a constant value here. If the mass is changing along with the velocity changing, then this actually doesn't work out. We need something more general. So this F equals ma really is for a special case when mass is constant, right? And our general case is something we're going to want. Now, this is going to work. We can say that the sum of forces acting on an object is your mass times your change in velocity. And if I just do a subtle shift in the way I write the equation, you start to see that momentum is creeping up here. And that's fine. It's all well and good. However, for a general sense of things, you would simply say change in momentum divided by the time interval. And the reason you just simply treat this delta symbol as its own variable and you can pull it out in front is because really what we're seeing is that the velocity could be changing. And that's true, but the mass could also be changing. And if you change the mass of a moving object, its momentum will be changing. Now, we probably are not going to be looking at situations where the mass is changing. It does match quite a bit what happens in real life. As you drive along the road in your car, the mass of your car is changing. You're using up fuel, and any remaining, any products of the combustion of the fuel are actually leaving. Your car loses mass as you drive. It's a slow process. It does not happen quickly, but it happens nonetheless. Imagine a rocket trying to deliver a payload to orbit. Well, the rocket is using up its fuel rather quickly. Its mass is changing quite rapidly. And so, yes, it is accelerating and trying to get to orbit, but it's also losing mass. The mass is changing, and so the momentum is changing due to two different components. Anyway, there is application in real life all over the place, but for most of our purposes, we're going to be looking at situations where mass is constant And it does work out. We can do a lot with this. So in this relationship, though, where we say sum of forces is equal to a change in momentum divided by the time interval in which this change takes place. This happens to be the original form of Newton's second law of motion. This happens to be what Newton said originally, that a net force acting on an object is going to change the momentum of an object. And in fact, the net force actually is the rate of change of momentum of an object. Fine. But rearranging this allows us to see something else. When we look at the change in momentum of an object, we can say to ourselves that it's equivalent to the sum of forces acting on it multiplied by the time interval over which those forces are acting. And it is this part right here. We know this. We would simply say change in momentum, and that's easy. It is this side of the equation here that is called impulse. And this word impulse is not one that's as readily known just in our society as momentum or energy or even work as a physics concept. It is probably better taught in lower grades in school than this idea of impulse. But here we go, and it is quite important. It allows us to further explore momentum and its applications. So here's what we're going to do. We're going to check out this relationship of impulse, and the way our textbook labels this, they call this momentum impulse theorem. And so come on, marker. There we go. This idea of impulse. The definition of impulse is that it is a vector quantity, and it is equal to what we're now going to have to call an average force multiplied by a time interval. And this is going to be equivalent to the change in momentum that an object will experience. Now, the reason for switching from a sum of forces to an average force is pretty important. The thing is, when an object is interacting with something else, and there's forces taking place, the forces are often not constant. In real life, the forces vary. They grow, they shrink, they disappear, they change direction all the time. And so if the forces are changing, you really have to simplify this a little bit and talk about the average force that's acting on the object. Average over time. As time goes on, the amount of force changes. So we must deal with the average. All right. So this is the idea of the momentum impulse theorem. You want to understand this idea of capital I. Now, when I write a capital I, I'm going to include the arrow above it, and the reason is capital I is used elsewhere in physics for other things, and with the arrow it will be impulse, always. This idea of impulse, we do have units. In the SI system, they are simply kilogram meters per second, just like momentum. And there's something else here. You should be saying to yourself, well, force times time. If you think way back in ancient history, we studied force times distance. And what a force times distance gave us was work, right? You should be seeing some similarities and be thinking a little bit of parallel things going on here between impulse and force times time compared to work and force times distance. Keep these relationships in mind. So we have impulse causing a change in momentum, or being equivalent to a change in momentum, right? Well, work, what we saw was that it changed something about energy, right? Let's not get into the specifics of your kinetic and potential and those things. But there is this work energy theorem. Work changes energy. There's this momentum impulse theorem. Impulse changes momentum. There are parallels. Okay. So we're also typically, and this is kind of important, we're also typically dealing with systems where mass is constant. Okay, so that's a safe assumption to make, unless otherwise specified. The mass of the thing you're dealing with will be a constant value. So here's what we do. We can say to ourselves, well, if we have any known mass and change in velocity, then we can find a change in momentum. And that's pretty straightforward. All we have to look at is this idea of any known mass and its corresponding change in velocity will be equivalent to a change in momentum, right? I'm just looking at the numerators in these two fractions, that relationship. And this is a very simple thing to see. And we'd have units here, again, of kilogram meters per second. But since we have this impulse momentum, or momentum impulse theorem, then this is also equivalent to your impulse. And so we'd be able to find that just as easily. Now, if we know the impulse, and we also happen to know a time interval, so with an impulse and a time interval, we can find the average force acting on an object. And that's going to be significant for us. That's what we're going to look at next, actually. So let's get to that example. There we go. So in this example, let's use a baseball example. I have a different sports example for you later on. And in the baseball example, let's say we'll look at a batter hitting a fastball. Okay, so we are going to have a baseball coming in toward the batter. Now, my artistic skills with the bat are going to be very terrible, very mediocre, so bear with me. I'm going to actually switch markers here. That was just not going to work out so well. So going thinner, baseball bat. Obviously also not drawn to scale. It looks more like a kid's toy, doesn't it? You get the idea. Bear with me. So we have the baseball coming in from the pitch. Keeping things simple, we're not even going to look at a curved path, a curved trajectory. Let's just consider, well, which way is the baseball traveling just before impact? And let's say it's traveling horizontally just before impact, just for simplicity's sake in this example. So it has an initial velocity in the horizontal direction, which means there is an initial momentum that we could define. And after the hit, okay, so this is our before the hit, and we're going to have an after the hit. Come back. Bat is going to swing, and bat. All right. Bat swung around. and our batter was able to hit the ball. So just after impact, this baseball is going to be moving away or back toward the pitcher, you might say. Let's again call this just after impact moving horizontal. There's going to be a final velocity, and therefore there's going to be a final momentum. And let's define a few other quantities. So we have a mass of the baseball, 0.145 kilograms. And if you actually were to look this up, I think it's pretty accurate. So the fastball pitch, that's our initial velocity. Fastball could be in the range of the 90 mile per hour vicinity. Let's call this one 95 miles per hour. This pitcher's got an arm, and he can throw. Well, we have to do something else here. We have to sort of say, is this going to be the positive direction or the negative direction? Remember, direction is critical to figuring out these problems. So, for argument's sake, just so we have it, let's say that the way I've illustrated it, to the right is going to be positive. That means toward the pitcher, or from the batter to the pitcher will be the positive direction. What that tells you is that this 95 mile per hour fastball pitch will be in the negative direction. And then also there's just after the hit. There's a final velocity. And a typical value here would be even faster, 115 miles per hour. And this is hit straight back out this way toward the pitcher. Initially, it'll be a horizontal direction. And of course, remember your projectile motion and those things. But this is just after the hit. That's all we're concerned with at the moment. That's going to be in the positive direction, so I don't do anything here. That is positive. But I have to recognize, okay, miles per hour, no, don't like that. Everything else I'm dealing with here is going to be in the units, the SI system of units. There will be some conversion I have to do. And when you look this up and you get the conversion from miles per hour into meters per second, you end up with 42.5 meters per second on the fastball pitch. And you end up, negative, that matters. You end up with the speed after the hit. I should say velocity because we are concerned with direction. 51.4 meters per second. Awesome. So we're going to be looking at the initial momentum, the final momentum. We're going to figure out the change and some other things beyond that. So here we go. Our initial momentum. Well, that's just mass times initial velocity, right? Very straightforward there. So our mass is 0.145 kilograms. And our initial velocity is the negative 42.5 meters per second. And so our initial momentum, is going to have a value of negative 6.16 kilogram meters per second. So we have that initial value. How about final momentum now? Be just as easy to find. Final momentum. Mass times final velocity. Mass hasn't changed. Mass is the same. 0.145 kilograms. Our final velocity, 51.4 meters per second. So our final momentum, we're going to get a value of 7.45 kilogram meters per second. Excellent. We went from an initial momentum of negative 6.16 to a final momentum of positive 7.45. Now, obviously, if we have our initial and our final, then what we're going to do with that is find the difference, and the difference is going to be equal to the impulse that acted on the ball. All right, so change of momentum is impulse. But that's really just going to be our final minus our initial momentum. And those values were 51.4 minus our initial was, oh shoot, oh, sorry about that. No. Looking at the wrong value. That was velocity. Our final momentum was 7.45. And I'm going to take away our initial, which was 6.16, but in the negative direction. Right? You can see why maintaining your direction sense, positive, negative direction, is really vital here. So the total change in momentum, or in other words, the impulse acting on the ball, is a value of 13.6 kilogram meters per second. So that's quite easily going to be a question you'll have to answer. What is the impulse acting on the ball in this case? That's 13.6 kilogram meters per second. No big issue there. Fair enough. And then you would say to yourself, of course, the next logical step is going to be, what is the average force acting on the ball? In order to find that average force, it requires that we know the impulse, and we do, but it also requires that we know the time interval. So let's say that our time interval is going to be really short. I mean, this happens in an extremely short period of time. And it's been measured before. You would find in the vicinity of 1.2 milliseconds is the time of interaction between the bat and the ball when this happens. It's a very brief period of time. But remember, we're going to be trying to solve for the average force. And from the definition of impulse, and also from the impulse momentum theorem, recall that impulse is equal to average force multiplied by the time interval. And I'm simply going to isolate average force. So I get impulse divided by that time interval. And I am able to work this out. My impulse was 13.6. My time interval was 1.20 milliseconds. So it's a very brief period of time. That, when you break it down, comes out to 0.0012. There's another zero there, just for significant figures, right? Seconds. This up here is kilogram meters per second. Yeah. Sorry, I was looking at the units saying to myself, well, wait. When I cancel seconds, I get kilogram meters, but that's not what's happening. We're actually going to end up with kilogram meters per second squared, which is a Newton, which is what we want for forces. Awesome. And so, digressing about the units, sorry about that. We do this calculation, and we get the awesome answer of, for sig figs, 11,300 newtons. Wow. Okay, so we have found the average force that's acting on the ball during its interaction with the bat. That's what's happening. And the crazy thing about this, I mean, this is kind of wild. This is huge. This is over 2,500 pounds. That's a huge amount of force. But it's acting for a very, very short period of time, remember. So one more thing I want to mention about this example is that you never see this. You're watching a baseball game on TV or in person. You never see this. It happens way too fast. But there's a cool picture in your textbook of the interaction between the baseball and the bat. And it was taken with a very high-speed camera to capture what's going on when they interact. So I want you to check out page 260 in your textbook for that cool picture of what happens to the ball while it's interacting with the bat. It's experiencing a huge force, its momentum is changing by quite a bit, and there's something interesting that you'll see in that picture. All right, so there's another example. You know what? This video is already going on long enough. I'm getting into another example. I'll keep it in a separate video for you. In the next example, we will look at a basketball situation. Thanks for watching. I will catch you next time.